Now in this slide we record a very important lemma which will be used in the proof of Riemann rock. You start with x, a smooth curve over K. So x is a smooth projective curve over K where K is closed. Now L, say, is a line bundle on X, and P is a point on the curve. So notice that a point on the curve is the irreducible divisor. Then Euler characteristic of the sheaf L tensor with O of P. This O bracket P needs to be thought of in terms of divisors. I will give its explanation later on at the end of the slide. So you have this point P here. Point P is a reducible divisor. So Euler characteristic of the sheaf L tensor OP is equal to Euler characteristic of the line bundle L, then plus 1. So you take a line bundle and you tensor it with O of P, you have to add 1. So this is very important. So proof is, first you start with an exact sequence of coherent sheaves on X. So again, this is part of the very important sequences which I have talked about before. In those very important sequences we talked about irreducible surfaces. Here the point is irreducible part of the curve. So we have this map. Now this O subscript P is nothing but a skyscraper sheaf. This is a skyscraper sheaf. So if this thing is like a curve X, this skyscraper sheaf is nothing but on the point P there sits the entire field K. So you have to think of the map from OX to OP as the evaluation map. You're taking these global functions, OX, and then you take open sets U, whatever functions there are, you evaluate them at the point P. So the kernel sheaf consists of precisely those functions which have X minus P as a factor, because when you plug in P you get 0. So let us write this down. It is precisely those functions which have X minus P as a factor. So again, OX to O subscript P is nothing but a evaluation map. You should think of like a stock OX comma P, then modulo out with the maximal ideal MP. It's some sort of evaluation there. This is skyscraper sheaf. So again, you take the stock there and then you modulo out the maximal ideal M subscript P. Basically it becomes a evaluation map at point P. Now you tensor above with the line bundle. So the line bundle locally looks like O of X, so this becomes a line bundle itself. We are more concerned with this part, L tensor O of P. What is this? Now, as I said before, this is nothing but L tensor with O X comma P divided by MP. I'll just write this down. So this is what it is. So this looks like a fiber of L at point P. So you tensor L with O X comma P, then you modulo out with MP. Now we want to determine its Euler characteristic. Its Euler characteristic is just 1. Yeah, so this 1 comes from the skyscraper sheaf K sitting at point P. So since we have just a point, so in the Euler characteristic you have H0, H1, H2. Only H0 contributes. Yeah, because it is just a point. So nothing comes from H1, nothing comes from H2, nothing comes from H3 and higher terms. Only H0 contributes. And in H0 you have that rust color sheaf sitting there, which is K, and that contributes 1. So now you just use the Euler characteristic of sheaf formula and you get this result. Yeah, so Euler characteristic of the sheaf in the center is equal to Euler characteristic of the sheaf on the left side and Euler characteristic of the sheaf on the right side. Now in place of L in this formula, if we just use L tensor O of P, you get the result in the lemma. Yeah, so just replace L here with L tensor O of P. So on the left hand side we will get Euler characteristic of L tensor O of P. 1 will remain as such, and then here instead of L, if you use L tensor O of P, tensor O of minus P, O of P tensor O of minus P will cancel out, which will just be left with L. Now we come up with an important definition. So again, let X be a smooth curve over K and D be a divisor on X. So the degree of D, so the degree of divisor D, which is given as D is given as summation of Ni Pi. This is nothing but sum of the coefficients. Now if the line bundle looks like O of D, then by lemma we will have so we define degree of L, degree of line bundle as degree of this divisor D, that is just you sum the coefficients of sigma and I. Now from the lemma we keep repeating the lemma for every point in the divisor. Yes, and then we add up everything to get this result. So in the lemma we were talking about a single point P. Now we add up for all the points in the line bundle, and this is what we will get. Yeah, so this one will keep adding up until you get all sigma and I. So you keep adding up A, so you keep adding up A repeatedly. For every point you keep adding it up. Now just to recall so that you make life easy, this O of D is actually given as this O of P1 tensor N1, this O of P2 tensor N2. So you could even use this directly. In fact, Hartshorne uses this directly and you get the result. So I think better proof is in Hartshorne that uses this result O of D directly, and then you don't have to add up every time. Now let us just recall what this O of P was. So this is rational functions on X. So this is rational functions of the curve X, so K of X, such that this divisor of F plus B is greater or equal to 0 on the open sets, and you also include F equals to 0. So what does this greater or equal to sign mean? That means once you take the coefficients and add divisor of F with 1 times P, all Ni are positive. Now what does this mean in plain English? It means all functions which either have no poles at all. So these functions have either no poles at all. So because we are adding 1 times p and having greater or equal to 0 sign, and if they have any poles, there is just one pole at p. So if they have no poles, everything is hunky-dory, it is anyway greater or equal to 0. And if they have a pole, that pole can have order at most 1, because then we will have -1 times p, and this -1 plus p will cancel out to get 0.